Okay, this is the last session. Okay, we learn how to sketch the conic sections. Okay, so we learn how to sketch the parabola, the ellipse, and the hyperbola. And based on what we have learned, we know at least there are several terms. That is the focus or foci in plural. You have more than one focus, and then you have directrix, right? And you have the vertices or the vertex. Okay? At least those three will determine how the conic sections will be shaping, okay? Or how the shape will be. Okay? Whether it will be the parabola, the ellipse, or hyperbola. And now we will move on to the next sections, which is the conic section, still conic section, but we are going to use polar coordinate system to make out the shape from these conic sections. Okay. So let me start with the let me start with the drawing. Okay, let me write this in terms of Cartesian y and x. Okay. So the idea will be the focus will be in the origin. Okay, 0, 0. That will be our focus. So maybe the conic section maybe around here. Maybe that is our conic. It can be ellipse, hyperbola, or parabola. Okay, this is just some part of the conics. Okay, now let me draw, or let me make out all the terms. This is directrix or L, or if this is at D, then this will be x equal D. This will be the focus, the origin, and we can take any random point at the conics, maybe here. This will be the P. And let me write this as radius. Okay. Okay, and then we can write theta in between the x-axis and the r. Okay. Let me write the theorem first, and then let me write how to get those theorem comes true. Okay, and what was its proof. So first, the theorem, we will say that the distance from P to F over the distance from P to L, the directrix, will be equal to some number that we are using a new symbols E. Okay. E means we call this eccentricity. So let F be a fixed point or focus, and L be a fixed line, or we call it directrix. Maybe this is not clear. This is L, and E is eccentricity. the conic is ellipse if e is less than 1, parabola if this e is equal 1, and hyperbola if e is greater than 1. So E, or eccentricity, is a ratio between the distance from focus to P and P to directrix. Okay. So we define a new term that is eccentricity. Okay. Now, if we look on the picture on the left, okay, we know that our PF, or the distance from P to F, is R. Let me write PF is equal R, right? And our PL, which means that this distance, let me draw the distance for you. This distance, this is PL, right? This is PF. So PL, if you look on the picture, PL means from F to directrix, that it's just D, right? This is just D. So PL means it will be D minus the distance from F to this P over here, right? This is R cosine theta, right? So PL will be D minus R cosine theta. And then if you let the PF over PL is equal E, and then we can try to manipulate the form using the definition we have. So we will get PF equal E PL, and we exchange all PF and PL with R and D minus R cosine theta. So this will be R equal E and then D minus R cosine theta. Let me write this in terms of, let's say we have first equation here. Okay, we will get back to this equation later on, but let me just take these equations and try to prove whether if we are using different E, it will have different shape of conics. Okay. So first, what we are going to do is we are going to square this equation. Let me copy this first. So this will be squared. Now this will be R squared. Okay. And we know that the x squared plus y squared is our R squared. Okay. So let us change the R squared to Cartesian x and y. And the term will be E squared, and then we expand the equations. That means this will be D squared minus R cos theta is x, right? It's just x. We change into the Cartesian. So 2 dx plus x squared. Now what we are going to do here, so every time we try to take some proof or manipulate some form, we need to have some goals, right? So our goals is actually we need to prove whether these three conclusions are true. Okay, so which means if you look on ellipse, we need to make out a form that is in ellipse form. So which means that we need to take this into this form and the other as well. Okay, so that is what our goal is. So from the polar, we are converting to Cartesians, and we need to take out the equations and then make out the ellipse, parabola, or hyperbola later on. Okay. So first, let's continue here. So first, maybe grouping all the components like x squared and x squared here. So this will be e squared d squared minus 2d e squared x, right, plus e squared x squared. And then we can have 1 minus e squared, and this is x squared. Let me move on to the left, plus 2 d e squared x plus y squared, and this will be e squared d squared on the right. Okay. It seems that we are almost there, right? We have x squared, we have y squared, right? At least if we want to make it an ellipse, this should be the important one, right? And now we have x here. If you feel confused, you can put your hand, cover this all the things here, and you can just see x and y. The other is just a constant, right? The other is just a constant. So first we can complete standard for the quadratic equation for x squared, right? Or if you want to maybe divide all by 1 minus e squared, it's much more easier. Maybe divide all with 1 minus e if you want. Okay, and then this terms here, it has twice as much as the form, right? So if we take this x, let me write here 2 d squared 1 minus squared x plus right? Okay. So we need also to plus the other one with plus. Or we can directly write that this will be x plus e squared d over 1 minus e squared and then squared, right? Or this should be squared. And then plus y squared 5. And then this will be e squared d squared. And because we already plus with this will turns out to be 1 minus e squared squared. Okay, I hope you don't get confused here. Okay, this is actually just using the complete standard form in the quadratic equation. Like this, if you have this x squared plus 2x plus y squared is equal something, right? You can write this in terms of x plus 1 squared, right? Okay, I hope you get this point here. So it's actually the same techniques for operating this. Okay, so if we take the if E is less than 1, okay, this is in fact is actually we can rewrite and compare with the ellipse. Okay. And then we can look on these two equations and compare, and then we can take some conclusions. That is, H is minus E squared D over 1 minus E squared, and A squared will be, or if you would like, all these terms we divide by this to make it 1, so that it will be equal with this. Okay. So that means that the A squared is the division of this one, right? So A squared will be E squared D squared over and B squared is E squared D squared divided by 1 minus E squared. Okay? Because B squared is having 1 minus E squared, so it's cancel the squared here, so it's just one term. But A squared, since we don't really have that one here, so we can write that whole thing from this one. Right? Okay. Or if you would like, I can rewrite this and maybe right here. If it doesn't seem to be, or if it's still confusing, let me write here and let me divide all with the E squared D squared, and then plus. Also divide the same thing. And this will be 1. Okay. So this will be A squared, right? And this will be canceling. So this will be B squared. And this will be H, right? Or minus H. Okay? Okay. And then from these equations, from A squared, B squared, if we still remember the C that is in C squared, this is A squared minus B squared. Okay? And from the look of the equations, we can take A squared minus B squared, and it will be equal with E with power 4 D divide 1 minus E squared squared, which means that this is actually similar to our 8 with squared, right? Oh, sorry, this should be squared. Or we can say that our C is equal with the minus H. And if you look on a squared and c squared, this and this, okay? If we divide c squared, divide with a squared, it will cancel like most of it, and we just observe that the rest is e squared, right? So we can also write that e is c divided by a. Okay. Okay, this means, okay, when we have e less than 1, we take this as a positive because 1 minus less than 1 is positive, right? Okay. If e is greater than 1, this will be negative. Right? And the same way, because it's negative, it will be minus. So it will be hyperbola. Okay? Right? If e is equal 1, this will be 0. This will be 0. And it's just something x squared with a constant. It's parabola. Okay? Got it? Okay. So from here, that this is actually can be proven with certain e from less than 1, equal 1, and greater 1. We can take out 3 possibility or 3 form of conic sections. Okay? Okay, but the most important thing is, aside from how to notice that this 3 terms here, I think this is by the end of the day in our conic sections. If we are looking the e, we can determine either its ellipse, parabola, or hyperbola by looking at e. Okay. But now there's another problem. Okay. If we know that it's ellipse, it's parabola, and hyperbola, how we design or how we decide whether it's looking like this or maybe on the right side, the bottom side, or the top side. Now there another method to look for. Okay. So E will be determining the shape, whether it's ellipse, parabola, hyperbola. It can be parabola, it's like this. It can be hyperbola if it has 2, right? It can be an ellipse if you connect all the things here, right? Okay. Okay, so let me write these equations one more. These general equations. Okay, if we take the solution of R, so R will be E D divided by 1 plus E cosine theta, like that one. We know that this came from these visuals, right? So directrix on the right, and then we have this on maybe around here. Maybe change a little bit. Okay. So this is the directrix. This is the conics, and this is the focus, right? This is our visuals like from the previous slides. Okay, now what's the difference if we have a similar, let's say, if we put the directrix on the left side. So let's say this is x equal d, not d, because it's on the left side, this will become negative d, right? Okay. Now, what's the implication of this? If you wrote the same method with the similar method with the previous one, you will arrive at the conclusion that this will be equal to r, okay, ed 1 minus e cos theta. Okay. Or if you still remember, in polar, I mentioned that there is a certain pattern with cos and sine. Right? This is cos with the positive. Going to be the right side, cos with the negative will be the left side. It's similar pattern. It's similar. And now you'll be able to determine what happened if I change this cos to sine. It will going to be cos and okay. So let me draw that for you. Now this will be ed over 1 plus e sine theta, and r ed 1 minus e sine theta. And how we get the sine is precisely the similar method. We will have the triangle from here. We have r, right? And we have this and you know that this will be r sine theta if theta is here. Okay, so let me write a conclusion here. That is polar equation form, or polar equation r ed 1 plus minus e cos theta and r equal ed 1 plus minus e sine theta. Both of this represent a conic section with eccentricity E. the conic is an ellipse if E is less than 1, parabola if E equal 1, or hyperbola if E is greater than 1. So basically this is the whole thing in these sections. The previous slide is just some proof of this this E and the polar. Okay, so basically what we are going to do is we will have some certain polar in terms of some constant here and maybe some equations at the bottom that it requires the trigonometric cosine or sine. And basically what we are going to do with those equations is we will convert those equations into this order. And we will determine how much is the E from that equation and how much is E. And lastly, we can sketch out the conics from this equation. Okay, so if you have like maybe R equals 6, 1 minus sine, okay, we will know for sure directly this will be parabola, right? This will be parabola. Because we can detect E or determine E from here. This is 1, so we know that it's parabola. And 1 minus sine, we look on the graph here, and probably it will look like this. But the question is, what will be the D? Because it has 6 and E is just 1, so we know that D will be 6. Okay. And similarly, if you have R, for example, this is 10, define 3 minus 2 cosine theta. So what we are going to do first is we'll look on the equations. All the equations, they all have constant 1. So let's make 1 for the equations. So let's make this 3 minus 2 cosine theta becomes, the 3 becomes 1. So let's all divide by 3. And we know that this E is 2 over 3, which is less than 1. That means that it will be an ellipse. And this terms is ED, right? So we know for sure this will be 2 over 3, D is 10 over 3, which means D is equal 5. But since it's minus cosine, it will be the left side, right? So this should be this one. This should be going to be left side. So this will be negative 5. Okay. So D will be negative 5. Or maybe not writing like that. Maybe writing in terms of x equal -5. And then how to sketch? We might use the some value, like maybe trying theta start from 0, maybe pi over 2, pi, and 3 over 2 pi. At least to get the line and the point. Okay, let me give you another example that is hyperbola. It's a little bit more efforts rather than the ellipse and the parabola, because hyperbola you will have two parts, right? Okay, now another example, if we have r is 12 over 2 plus 4 sine theta. Okay, maybe if you would like to try first. And notice that in hyperbola, you will have the asymptote, right? How to get the asymptote? First, remember the definition of the asymptote. Asymptote, it came from when you have the curve like maybe here, right? And when you have this, it's going to have more and more and more, and it turns out to be, you can draw some line like it happened in tangent, And remember, you also learn about the asymptote in terms of limit, right? Limit. The vertical asymptote, we can think this in when you have some x limit, maybe going to be approaching a. Maybe this is 1 over x, maybe. And this will turns out to be maybe plus minus infinity, okay? Well, of course, maybe not a, maybe just 0 to give you an easy way to look at. Maybe 0. When this happens, then you know that the limit is on x equals 0, right? Or the asymptote is x equals 0. The same way we will use that in our equation here. So we are going to use the limit when this term's going to be 0 from the right or from the left. And we can just pick each one. But before that, maybe we can just let the r becomes 6 and 1 plus 2 sine theta, right? Which means that this e is 2. So it should be a hyperbola, right? This should be a hyperbola. And e multiplied with d is 6. So d is 3. And since it's plus, so x equals 3, so at the top. So at least we want to draw maybe here. We draw the first one over here, probably. So this will be y equal 3, the directrix. This will be 0. And now, to make sure that this is correct, actually we need to have some table value of theta and some r. We can have theta from 0, pi over 2, pi, and 3 over 2 pi. And we just plug into the equations. This will be 6. Pi over 2 which will be 1, so it should be 6 by 3 is 2. Pi will be 6, it's 0. 3 over 2 will be a negative, so we will have a negative 6. So this should be 6, 0, right? Start from the right, from the angle 0, and then we move to pi over 2 is around here. That is 2 pi over 2, and 6 will be here. And 3 over 2 pi will be negative 6, right? And how do we write negative 6 in terms of polar? From here. Where is it, right? If we, this is combination of Cartesian and polar. So the point I'm writing in polar. So we start from here, going here, going here, so pi. And if we want to make 3 over 2 pi, it should be going down here, right? This is negative. So where do we should put our negative 6? Yes, here. And that will be our another hyperbola. Okay. And remember that we can write the, so if we have negative 6 3 over 2 pi, this will be equal with 6 and pi over 2, right? The difference is pi, right? Okay. Okay, so we can write here that this is the 6 and pi over 2. And it should be same curve like that. But to make sure that this hyperbola is correct, and actually my drawing is not really a hyperbola, it should be a little bit more having more acute like that. But anyway, if you want to be more accurate, you can also check the asymptote. You can check the asymptote. How to check? We can write the equations first. Write the equations are 6 divided by 1 plus 2 sine theta. Okay. We will have r going to be positive or negative infinity if 1 plus 2 sine theta is going to be 0 from the right or from the left. But anyway, if we let this, then we know that this sine theta will be negative 1 over 2, which means that the theta will be 7 over 6 pi and 11 over 6 pi. So if we are looking on this graph, the asymptote should be having two asymptotes here, right? Should be crossing at the middle point. So let's imagine the middle point is actually not really here, it's going to be here, the directrix. So the asymptote will be in the middle here, right? That is the cross sections. That is parallel. Okay. So if the 7 over 6 and 11 over 6, maybe it's like this, okay? Then the asymptote will be parallel with those lines, with the angle from here. So we can draw the asymptote. It's not really straight line, but yeah. Anyway, that will be the asymptote. So asymptote will be parallels with theta and theta. Okay, we can have some short break. Okay. So we have discussed the polar, okay, in conic section in polar. So the important thing is to define the eccentricity and to define this polar the polar curve, this ED over 1 plus minus E cosine theta or 1 plus minus E sine theta. Okay. And from those four, we can define which way our conics will be. Okay. And this is the last thing, but probably quite important, but not as important as the first one. But let me just write this. If we can write r in terms of a function of theta, which is we can define this as ed over 1 plus minus e cos theta or sin theta, right? We can also define, if we have r and then f, and then the theta is changing around some angle alpha. What is happening now is we are rotating our curve, okay? Because this is in polar, we rotate our curve, right? How about the rotation? Is it going to rotate clockwise or counterclockwise? Okay, the key to understand which way is if you know the transformation of functions. Like if you have y equal x squared and y equal maybe x minus 2. This means that it's shifted to the right or to the left? Right. Okay, right. So how about this? Counterclockwise or clockwise? So it's the same, it's similar, it's not really the same, but it's similar a similar behavior. Okay? So if we say that this is going to the right, and you know that the polar, if you plus the angle, it's going counterclockwise. So it's going to be counterclockwise. Okay? And it's the similarity. If this is x minus 2 is going to the right, like we plus the x, right? This is also minus, so we should do the plus. The rotation should also do the plus. Okay, this is similarity. So it means that we will have rotations. So rotate our curves counterclockwise. About origin through angle alpha. But the curve itself, it will be perfectly the same as when we are not rotating. Okay. So if you get the idea of this theta minus alpha, maybe if we have like this one, if this is maybe theta minus pi over 3, for example, then it means that we need to rotate this hyperbola pi over 3, maybe around. Maybe if this is the angle that is still without any rotation, that we need to take some angle pi over 3 here, and then this will be going to rotate over there. So this will be our new axis. Okay, new axis. But of course, that will be really complicated if you are just using your pen and paper. At least you need to have some ruler that has an angle, certain angle in your ruler. And another applications, okay, so aside from you can rotate this this polar, the application of the polar is let me write here. R is, we know that ED over, let's say we have 1 plus E cos theta. Okay. in some astronomical calculation or analysis, we can write ED in terms of A and then 1 minus E squared. So what is the, this means, okay, so if I have some orbit, and this is a planet, and this is a theta, and this is r. This is the center, which is the sun, and the closest distance we call the perihelion. Helion means from the sun, okay? And aphelion is for the furthest one. Peri is in perimeter, the closest one. So the perihelion will be A 1 minus E, and the aphelion will be A 1 plus E. And A itself, we call the A as semi-major axis. A is called the semi-major axis. But this is just additional information. Just additional information. And how, at least if you want to know why this difference, this is in terms of at theta equals 0. This is at theta equal pi. At theta equals 0, our cosine will be 1, right? Will be 1. Or it's just 1 plus E. And we know that this 1 minus E squared can be factorized, becomes this. And depends on this cosine, whether it's positive or negative. We will know that it will be 1 minus E like this perihelion, or 1 plus E this aphelion. It depends on how the theta will be moving. Okay. Yeah, I think that will be the last one for the chapter 10. So yeah, if you maybe have interest in planetary system or in astronomy in general, it would be also better if you know like how we can get the formulations, like why we think that the elliptical orbit is a better way to approach our universe. Maybe if you have a chance to look on the, like using some special telescope to look on the planet outside. I think if you have a chance, it's a really good experience. And also it's like when I was maybe still kids, always wondering how we know the distance from Earth to some planets, right? Or maybe to sun, how we can compute that. Through some formulations and some polar curve, we know how. But sometimes there will be some slightly error because it's based on simulation. So we are not actually we are still not sure whether it's the real distance or not, because there are a little bit of unknown, right? Because the farthest distance that we have traveled so far is maybe having the robots on Mars, right? The robots on Mars. I think the other one, not sure, right? I think that the robot, the Voyage in Mars, and they have the transportations to the capture. But I think that's also the dream for, I think, Elon Musk, right? He wants to take human to Mars, right? Not sure. But do you remember, I think last year or maybe 2 years ago, that at the first stage of COVID, I think, the NASA, or I'm not sure which institution, that they released the footage of the UFO. Do you still remember? Before that, people said that, oh, it was just hoax, blah blah blah. But then those institutions, the NASA, they released like the blurred object on the sky, right? So I think maybe they know something but we don't. Okay, anyway. Okay, any questions from this conic sections in polar and also the previous chapter 10? No? Okay. Okay, we move on to new chapter 11. So I will have some introductions, and then we will continue chapter 11 next Monday a little bit, and then we go to some review for chapter 10. And I hope you get another chance with your TA on Thursday to have also some exercise, and we will have quiz next Friday. Okay, we'll have quiz next Friday. Okay. It will be chapter 10, about chapter 10. Okay, so let me start with maybe take a new page. So chapter 11, we will deal with this sequences, series, power series. But let me start chapter 11 with the sequence. And I believe most of you guys are already familiar with sequence. So basically what sequence means is, if you have a list of number, okay, if you have a list of number and you know that you can take that list and make some formulation about the list, and maybe it has some patterns or any obvious formula, then we can take those into some formulation. So we can write a sequence. We can write like this, or we can write in terms of general terms A-N, or we can write in terms of, we have maybe writing n is from 1 to some infinite number. So n is the integer that is denotes the terms of the sequence. So we call this as the first term, so the first, the second, and so on. Okay. We usually assuming that it should be started from n equal 1. That's the default, unless maybe mentioned in another n. But usually we start from n equal 1. So let me write here. Usually n starts from n equal 1. Okay, so if we have like 1 over 2 with power of n, which means that this will be start from half, from n equal 1, and then n equal 2, n equal 3, n equal 4, and so on. We can also start the sequence from any n we want, maybe n equal 2. So if we start from n equal 2, this will be start from 2 over 3, 3 over 4, 4 over 5, and so on. Okay? And also, we can have the alternating sequence. If we have, for example, -1 with power of n, and then maybe n plus 1 over 3. Maybe start with from 0. Okay. This will generate the sequence that is start from 1 and then -2, 3, -4, 5, and so on. So notice that you may have alternating sequence as in the signs of the sequence itself. So the sequence will have positive, negative, positive, negative, positive. Or maybe negative, positive, negative, positive is also possible. It depends on which n we are starting or which formulation. It can be -1 with power of n, or maybe you have like n minus 1 or n plus 1. It depends on the formula. Okay? But when you look on the formula, if you have minus 1 with power of something, then it should have the alternate sequence. So that's the alternate sequence. So for example, if we have the pattern that is start from 3 over 5, -4 over 25, 5 over 125, -6, 6 to 5, and so on. So the general formula for an is, okay, we can check. A1 is 3 over 5, right? A2 is -4 over 25, and so on. And because we know that there is an alternate sequence from positive, negative, positive, negative, maybe we need to start with -1 with power of something. Let's say we can have n minus 1, or maybe -1, n plus 1. Because this -1, just to make sure that it starts with negative or positive. Okay. If even, that will be positive. If odd, then it will be negative, right? Okay. And then maybe we can take the first one, n minus 1. And we start from, let's say, 1. We start from 1, then it will be a 0. It should be 1, right? It should be 1. So it is still okay. And then the next is for 3 over 5, 4 over 25. So if we look the equations, or if we look the sequence, it starts from 5 and then it's multiply. It's multiply. It has some certain 5 with power of something, right? So it's start from 5 with power of something, according to the n, right? And then the top equation is just n plus 2. And we know that this will be the general equations. Okay? And I hope you are familiar with how to formalize the sequence, okay? And take it in the pattern. Okay. However, we also have some sequence that they don't have a simple defined equations. Okay? For example, the Fibonacci, I think most of you are familiar with. Let me write Fibonacci sequence. So it's defined recursively by conditions, that is, we need to state the first two terms, and then the formulation will be start with some summations of the previous two terms, right? And n should be start from 3. So it will start from 1, 1, 2, 3, 5, 8, 13, and so on. And it's one of the because it's really different, and it's not really simple to define, but it has some certain natural way that you can find in nature. Fibonacci becomes more popular, right? Popular. But this is just to show you some examples. Okay. Okay, I think we can move a little bit. Okay, by looking at the sequence n over n plus 1, okay, if we look one by one, the order start from half, 2 over 3, 3 over 4, 4 over 5. What I want to make here to show you that if we try to draw in a line number what the sequence will be, okay, let's say this is our line number, start from 0 to maybe 1 here, okay. Then we will start, there will be in the middle, this will be A1, right? This is A1, A2, A3, A4, and so on. That is half in the middle. And then 2 over 3, maybe we divide with 3 parts, and then it will be showing maybe around here. This will be A2. And then A3, maybe around here. And then A4, maybe around here. And then A5 maybe around here, A6, and you'll see that there is some slight portions that is, they are going to be getting closer to some number 1 here. For example, if we have n equal 99, n equal 99, we will have 99 over 100, right? Which is very close to 1. If we have 9999, it will be 10,000, right? So if we increase the n larger and larger and larger, we will see that it will get close to 1, but it never have been to 1, right? It will be just as close as it is, it will never be 1. Okay? So how do we solve this? How do we solve this? Limit. So if we have something closer to some value that we are sure that it will going to be nearby this number, we need to have the limit concept. Okay. So this will be the limit of a sequence. This is to note that, or to conclude that the sequence may have some value that will be, that if you increase the integers, if you increase the n, it will be getting closer to some finite value. Okay. Like in our case here, it will be getting close to 1, right? Or if we draw in more clear picture, as in the Cartesian, let's say this is our an and this is our n, and if we take this line, this is a value of 1, and maybe taking n from 0, 1, 2, 3, 4, 5, maybe 6, maybe until 6. Maybe for 1 it's getting half, 2 is getting closer, closer, closer. Okay. And let's say that's 6 over 7. So if you look here, it's similar to what we have done in limit, right? Okay, if we take the difference between 1 and the patterns and the sequence, the difference (1 minus n over n plus 1) is just 1 over n plus 1. So the difference is just 1 over n plus 1. So as n is getting bigger, or we can write as n getting to some infinite point or infinitely large. So by taking n sufficiently large, we can write that the limit as n approaches infinity of n over n plus 1 is equal 1. Or in general, we can write limit as n approaching infinity of our sequence will be equal with some L. So it means that the sequence will approach L. Or we can write an getting closer to L as n getting larger. And if the limit exists or having value, we say an is convergent or converge. Otherwise, if it doesn't exist, we say the sequence is divergent or diverge. So converge and diverge, as in the literal meaning, converge means it's converged to or focus into some value. Diverge means it's spread out. Okay. Okay, just some illustrations, okay, just some visuals that for the convergence Okay, let's say this is from here, start from here. Okay, we can say also this is converge as n getting larger. So we can say this is also converge as n getting larger. And if we have some oscillations, if we have this kind of changing its way, like for example like this, we can also say this is converges. Although we can see that it's up and down, but the oscillations getting, the gap getting smaller, and it goes to some value L. So we can also say that this is a n limit. This is also going to be L. Okay, now there are some another definitions. We call it the precise definition, but since in the last semester I didn't really elaborate on precise definition, let me just make a shortcut, okay, to explain what precise definition of limit means. Okay, so if you remember that if we have some random functions like this with some discontinuity at the middle, and if we evaluate this at x equal a, okay, and if this is having some L value, we know from the limit concept that this will be, if we have limit as x approaching a of some f of x, this will be equal L. So this means that if you remember the left hand limit, right hand limit, right? Okay. Now the problem with this definition is there's still some confusing terms in limit because we are not really sure how close this x to a. Okay. We just say that as x approaching a, how close between x and a. Now, to solve those problems, we invented a method or a proof by using some small numbers, another symbols that define how close a with those numbers. Okay, let's say the numbers for a, the close is the delta. So we have the distance here. Okay. This will be, say, the delta. So this is a plus delta. This is a minus delta. So the distance will be delta. Okay. And because of this, then we can take these two distance, take it to the functions, and we know that there will be another distance between L. So from the distance of delta, we are having another distance in L here. we call the distance is epsilon. Okay. So we call the distance here epsilon. So this is L minus epsilon. This is L plus epsilon. Okay. So by doing so, we are going to prove whether our delta can get precise epsilon. So this means that this distance should be less than delta, so, or then, maybe then. So if, and then, there will be some distance here that is less than epsilon. This is the summary for percentage example. There are some certain points that is in between, but at the end of the day, this is the idea. So which means that although we are introducing delta and epsilon, which is some random small numbers, but this is actually giving you the idea that if there is certain delta that you think, then if you put that delta inside this equation here, and maybe you can prove it that using some certain delta will prove that there will be an epsilon. Okay. The delta can be any numbers, and this can be any random functions as well. So that's the summary for percentage. Okay. And in the sequence, it will be similar. So in sequence, we can write this in sequence. Okay, so precise definition of a limit of sequence. Okay, so let's say our sequence has limit L, and we write limit as n approaching infinity of the sequence is equal L, or we can write an going to be L as n going to be infinite. Okay, and this will be true if for every epsilon greater 0, every positive epsilon. Remember, this is the same epsilon as we mentioned in this previous here, which means that the distance, okay, the small distance. So for every epsilon, there is a corresponding integer n, such that if n greater than the small n greater than the capital N, then this always happens. The distance from sequence to those value L will always less than epsilon. This is precisely the same meaning what we have done here, but it's in terms of sequence. Okay. Well, we can also write in terms of delta, but I don't think that's helpful. But you can also write like in terms of this. But since it's sequence, and we are just using the integer 1, 2, 3, 4, so I think that this is just okay. So no matter how small the interval, okay, the interval between the L and the sequence, which means the L minus epsilon and L plus epsilon, there will be the integer, that's the capital N, that will be exist such all terms of the sequence, it will be on those intervals. Okay? Or if we try to illustrate, if you look on your textbook, there's some illustrations. So if you have a sequence that oscillated, so maybe from here to here, but then it will be going to be smaller, and it is going to be here. So we start from 0 and maybe go to A1 and then A2 and then move back a little bit and then move forward, maybe here, really forward, A4, and then move backwards, and then maybe forwards, is A7, but then later backwards here. And then the next one is maybe around here at the middle. Let's say this is our L. It's getting close to L. Okay. So let's take the L minus epsilon here, L plus epsilon here. Although it's looking bigger, but let's say that that's our epsilon. And let's say this is 2 of our n plus 1 and n plus 2. So it's always that the distance n, or the number capital N, is always nearby the L. So no matter how small the interval we have, there will be some capital N is always nearby this L. Or maybe if this is confusing, maybe if we look on the Cartesian. If we look at the Cartesians, that this is n, and maybe this is an, and this is L. So we start from maybe 1 here, 2, 3, 4, and then 5, maybe going there. Okay, maybe it's going to have some L like that. And then if we take this line and this line to denote that there is some epsilon over there, which is this is L plus epsilon and L minus epsilon, which denotes some small distance between L and the L plus epsilon, but the distance is epsilon. So if I take some number n, maybe here, so if we take this and looking on how this n will be interact with the L, you see that this capital N here, so the points will be line between this, the green color line, right? They will always getting in between of L plus epsilon and L minus epsilon. So if n is greater than n, the an must be in between L plus epsilon and L minus epsilon, or the interval directly. We can write this. And this must be valid no matter how small the distance. Maybe if we increase still, it should be in between those. saying that there will be some small distance. Epsilon. We can call it epsilon. And of course, it will be diverge if they are not approaching a single number. And there's another point that it is still in precise definition, but this is for the for infinite limit. So limit as n approaching infinity of an, this will equal infinity, means, okay, for every m, there is integer n such that if n greater capital N, then an is greater than capital M. And this is also the same if you approach negative infinity. Okay. This means, okay, if you maybe feel confused on the words, this means that M is any random point or any random number that you can think. But this means when you increase the integer, like A1, A2, A3, A4, A5, if you have the infinite limit, if they behave as infinite limit, then no matter how you put your n, your an is going to be greater than those n. It's always getting increased when you increase your integer. It means that, it's always getting increase and increase and increase. It's going to be increase, 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 and you will not be able to note, or it will be not getting any closer to some number because it's going to be infinite. So no matter how you put your m, your an is always greater than n. Okay, I think I will just finish up until here. Okay, and next Monday we can move on to property of convergence sequence. Property of convergence sequence. And basically that is limit property. So I hope you still remember some of the limit property, limit law, and then squeeze theorem. Okay. So yeah, I think we finished today.